Okay, so we have very few people, so I hope people will join in the meantime. Let's start the class. So I would like to welcome you all to the week 4 of this doubt clearing or problem solving session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor NP Padhy and Professor Premlata Jena. I am Swastik Sharma. I'm a TA for this course. Uh, yeah, so let's start. Let me share my screen. Hmm. Okay, so um, just a second. Yeah. So last week we discussed about energy storage systems. The whole build up towards the smart grids is how they are becoming smarter, right? So how they are getting the brain of their own. So the by smarter we means we are challenging the precedences set by the traditional systems. Like for example, the power will only flow from transmission to distribution side, right? Uh, but now distribution system is also becoming more active in nature. Earlier it was supposed to be passive, where we were only supposed to be consumers of electricity, but now we are producing as well. We are producing as well as we are consuming, and the correct term for this is prosumers, right? So now, because this is happening, DIAs are becoming more and more prevalent in the distribution side, and we have renewable energy integration at the transmission side as well, where we have solar energy, wind energy, right? So what this has done is this has made our power systems more and more the complexity has increased. So before we were able to monitor the grid entirely as being the steady state observers of the system, but now the dynamics have changed, and to model this dynamics, to monitor these dynamics, we have to now shift, or it's like, for example, you get a software update for your mobile phones, right? And something like this has happened to monitoring as well, and now we have shifted from being the steady state observers to becoming transient state observers also of the distribution system, right? And all this is just to visualize the dynamics of operations, right? Just remember the word that dynamics. So to be able to observe, monitor these dynamics, we have to now rely on systems which are called wide area monitoring systems, right? So what in effect, what do they do? It's a collective technology to monitor, it's a collective technology to monitor the power systems, where where we are now shifting our focuses from just having remote terminal units to having phasor measurement units, where we can measure phasors, which will be able to help us in deriving all the other quantities of interest, right? So what we want is we want to observe the state of the system at very high resolution. When I say high resolution, it's that I can see the state of the system at any given point of time for any given duration of the time, right? So like for example, when we had SCADA, it collects data every 1 or 2 seconds, right? So it's like between 1 or 2, our system state can change, right? There can be many transients happening, some fluctuation, something, right? For that, we need to have more resolution of samples coming per cycle or per second, right? And for that, WAMS, which employs PMUs, is able to collect timestamp data for 10 to 60 times per second. So I've already discussed what PMUs are, but still, for people who are new, it's PMUs are phasor measurement units. Their job is to measure phasors. So now people can say, what is phasor? Phasors are nothing but rotating vectors, right? So they have a sense of direction as well as a sense of magnitude, right? So now VAMS is coming into picture, right? This wide area monitoring system. So we want to sit at a remote location, and we can see how our system is behaving at millisecond, or milliseconds of the some milliseconds of the timestamp, right? Then we can get all of this data which is time stamped according to a global positioning satellite or a GPS clock, right? So this can help us monitor the system remotely. That is why it's called wide area monitoring system, right? We can monitor a very wide area using this setup, right? And this is what we call essentially a real-time monitoring of the system. So in real time, we can monitor the state of the system at any given point of time. Right. So when we say monitoring, we say that we can monitor the real-time updates in the system as and when the data is made available to us. VAMs can also be used in post-disturbance analysis, right? For example, we want to see how a fault has progressed, which has caused some disturbance into the power system, right? Because my data is not time-stamped with the GPS, and it is a sequence of data, right? Sequence of data which has timestamps with it. Like for example, when I say timestamp, what I mean is, let's say some quantity changed, right? And we know when it changed, which is the time at which it is synced to its global positioning satellite, right? For example, at 12 p.m. 3 seconds, 1 minute 3 seconds and 30 milliseconds, something happened. So we can know from the sequence of data, it becomes very easy for us to do post disturbance analysis, right? Next, we can have protection. When I say adaptive protection, what I really mean is that because we have PMU, because we have transient observability, I'll come to this transient and steady state in a bit. But what I say is we can monitor the dynamics very closely, and that's why we can have adaptive protection schemes enabled due to the placement of these PMUs. This can also be used in restoration activities, right? For example, if you are trying to restore your system, right? So let's say a blackout or a brownout has occurred, and now you want to restore your system. The system has now system was completely shut down, and now you want to uh, restore it to back to its normal operation, right? And for that, the sequence of data, how system is responding, at particular milliseconds, that you can do because you have such high resolution, 10 to 60 times per second. So that is the one major application of this VAMPs. And the last is controllability. Controllability in a sense that a system controller sitting at a remote location can have complete observability and controllability at any given node of the system, right? Now, one important thing that I want to mention here is that this SCADA, it measures or it collects data for every 1 or 2 seconds, right? So the resolution is very less. So you have to wait for every 1 or 2 seconds to get what is the state of the system and what it gives you. SCADA is generally used to give specific quantities to you, right? And these quantities are your voltage magnitude, your power injection or Q injection, your power flow, and Q flow in a line, right? So this is the data given by this is the data which is given by or collected by a SCADA through RTUs, remote terminal units, right? But WAMs which employ PMUs, they get only two kinds of data, right? These are phasor quantities, which is I'll write it separately. PMUs give what? Phasor quantities, which is current, voltage and current phases. And when I say voltage and current phases, so even if you have only voltage phasor, you can derive any quantity from this phasor, right? When I say any quantity, your injections, your flows, you can derive. Now, let me tell you how. So people, oh sorry, this is not correct. Just a second. So some of you are maybe familiar with this, but still for those who aren't, I'll just give you a quick overlook on how this, having known just V, you can know the entire state of the system, right? Now we know according to the apparent power of the system at any given bus I. If I want to calculate the apparent power injected at this bus I, what I need is your Vi and II complex conjugate. Both of them are in phasors, right? Phasors, when I say phasor, your V angle phi and I angle phi, right? This can be written as V cos phi plus J sin phi, and similarly this can be written as I cos phi and J sin phi, right? So when I say you need only V, let me tell you how. Let's say I, right? So how can you represent current injected into a bus? It's just, you know the network, right? When you know the network you are operating, you can easily get your admittance matrix, right? Bus admittance matrix. You know all the things, right? Rij, just a second. Yeah, you know everything, your resistances of the line, your reactances and everything, right? So these don't change. These quantities normally don't change. For a network, they are fixed, right? So you know this quantity, this is fixed for you. So if you want to see how it is incorporated, it's like this. For all other nodes except for I, right? Yij, Vj. This is how it is written, your current injection. And if I substitute into this equation, what I get is Vi Vj star summation of j equals to 1 to n Yij star. So knowing only the voltage phasors, you can derive anything, your current and then your apparent power. Even you can derive your power flow between two lines, which is what? Vi Iij complex, and Iij complex is nothing but summation of j equals to 1 to n Yij Vj minus Vi, right? So any given quantity you can derive by knowing only the sorry, this would be Vi minus Vj, right? Any given quantity you can derive using your phasors, and these phasors are essentially on the only quantity that is required. That is why in state estimation, which you will see in future classes, state estimation, you only need to derive two quantities, which are voltages at bus and your phases or phase angle at a bus, right? These are the only two quantities which can tell you the state of the system. Rest all other things are derived, right? And let's expand this for your. So how will this be written? This will be written as summation j equals to 1 to n mod of Vi mod of Vj mod of Yij at an angle of theta I minus theta j minus delta ij. So this is how your load flow equations are also derived. So if people are familiar with load flow equations, this is very easy for them to use, right? So when I say phasor quantities are just the only quantities that can help you monitor the state of the entire system, and that is why PMUs are, generally considered to be much more or much better substitutes to your RTUs or SCADA. Right. This is how the WAMS, when I say WAMS, it's wide area monitoring system. The structure is something like this. So you have PMUs placed at your transmission side, right? I should use this. So you have PMUs at the transmission side, right? These transmission sites have PMUs, and what they do, they get phasor values from these phasor estimates from these nodes, and they supply it to a super PDC, which is called PDC is nothing but your phasor data concentrator. It is used to, as the name suggests, store all the phasor data coming from PMUs from connected across the entire region. And you can see one more thing, that there are local PDCs as well. So you can have sometimes, for example, if there are multiple PMUs connected at same, you say, what can I say, at similar buses. So you can have a hierarchical structure where you can store it at one place and then communicate that stored value to the super PDC as well. That is why there is a difference in name. One is called super phase data concentrator and one is local data phasor data concentrator. When it comes super, it means it covers the entire geographical region. You can also see one thing, that there is this micro PMU. At the distribution side, whenever you see, there are micro PMUs. So why are they called micro? It's because of the fact that at transmission side, your voltage levels are very high, right? But when you come to distribution side, it's 11 kV, 3.3 kV, 400 volts, and even sub distribution setup, right? So what you can do is you can have multiple micro PMUs connected to this node, where these can store this distribution data, and we call them micro PMU because they have a resolution which is much more than your normal PMUs. When I say much more, so I said 10 to 60 times per second for PMUs, right? For micro PMUs, at least the one that has developed by IIT Kanpur, it's 100 samples per second, right? So the resolution is much more when it comes to PMU, and it is needed because your DRs are connected mostly to the distribution side, and that is where you feel most of the fluctuations happening. And since the voltage level is low, to catch that fluctuation, you need much more smaller resolution, much more higher resolution of your PMU, and that is why they are called micro PMUs, right? So these super PDCs are then connected to, control centers where we can monitor everything. So we have this kind of like a super PDC at it can be said that NLDC, or National Load Dispatch Center, or POSOCO, which is also called in New Delhi. It can be said to be containing this control center, which is connected to this Ethernet based communication protocol to your super phasor data concentrator, right? So you see, you your phasor data, your sorry, whatever phasor data your PMUs measure, these go through a hierarchical structure where there are first stored at the local PDC and then transferred to a super PDC. So we'll see their structure in a bit, but I was just interested in letting you know about this, right? Now, there are some benefits, as I already told you in previous slides, that the PMUs provide wide area situational awareness, and it can improve visibility as well to dynamic conditions. When I say dynamic, as I told you, SCADA collects data for 1 to 2 seconds, while for VAMs it can collect data for 10 to 60 times per second, right? So when you have more data per second, you can have much more, you can have a higher transient or dynamic observability, and that is why your PMUs are much more important. Also, it can determine stress points of the electric power system. When I say stress point, let's say the PMUs, these are costly affairs, right? You don't want to, you cannot just place it at every node and be like, okay, I can get all the data from every node. No, people normally don't do that. It's a costly affair. So your PMUs are generally placed at those locations which are prone to faults, prone to stresses and stuff like that, right? And because they have these dynamic observability or transient observability, they can determine what stress points your electric power system can have, right? And because these are instantaneous in nature, you can have much more resolution of data coming per second. They can provide early warning detection alerts that SCADA can miss. As you can see in this diagram, you see, SCADA has steady state observability. When I say steady state observability, it doesn't know what is happening in between in between the points it is collecting data from, right? It's just simple value. Even when there is a peak, a negative, some load fluctuation happened, a negative side, there is a peak, right? And it is not able to detect this. Similarly, here, and here. So this is where PMUs can come into play because the resolution is much more. Also, since you have PMUs, you can have more data, and you can employ this data using some big data analytics techniques such as machine learning, or some artificial intelligence technique, where you can use this data to generate some kind of a short-term load forecasting data, or you want to develop some algorithm to have better observability. So because you have data, you can do you can analyze this in a very, in a way which was not possible because for the same time period you have more data compared to SCADA. And using this, you can help prevent outages by properly identifying the time periods at which by identifying probable outages that can happen during the system's behavior, right? So some of the applications this PMU has, sorry, transmission system monitoring, then you have distribution system monitoring and DER monitoring. So at the distribution side, as I told you, now we have shifted from the earlier stage where thought only power will flow from top to bottom, that is generation to distribution. Now distribution is actively participating in this power production scenario too, right? So now we have a bidirectional power flow, and for this we need micro PMUs or these PMUs at different side to be able to check how the transients are behaving due to this new addition into the power system. And that is where PMU find this application, right? So this is something that I got from the slides. So as you can see, the resolution, you have one sample every 2 to 4 seconds. That is why it is called steady state observability, as I was saying it till now, because you only know the steady state of the system, not the transients, what's happening between microseconds or milliseconds. While because you have 10 to 60, you can have dynamic or transient observability. You can know what are the how the dynamics of the systems are changing or behaving. You can only measure magnitude, as I told you. You can only measure the magnitude of voltage, power injection, reactive power injection, line power flow, or reactive power flow, right? But now you can measure magnitude and phase angle, because you have this phasor phasor quantity which can have phase angle attributed to it as well. So you can have both. And SCADA generally newer age RTOs do have GPS compatibility where they can synchronize, but generally the older versions didn't have time synchronization features, while this had. Your total input or output channels were more in SCADA. You had 100 plus analog and digital uh, uh, channels, where in PMU you can have 10 phasers generated for 16 digital and analog pins. Basically, SCADA was used for local monitoring and control, while PMUs can help you in wide area monitoring and control. That is why it's called WAMs. Just a second, let me think if I missed anything. One thing that I wanted to talk. Yeah. So let's discuss about the structure. So when I talk about WAM structure, what we require for a monitoring system, two things are required, right? Mainly, you should have data coming from resources, right? You need resources for data. So data resources, and you need a communication system, without which you can't have wide area monitoring, right? Sitting at a remote place, you can't have a complete observability of the entire network. For that, you need a proper communication system with resilient communication system, as I should say, right? Now when I say data resources, there are two kinds of data that comes from these WAMs, which is an operational data, and then you have non-operational data. So when I say operational data, you want to have a continuous stream of data coming, that is continuous data. You know, why you need continuous data? To have to know how the system is behaving, how the system is operating, and that is why it's called operational data. And what kind of data can help you monitor the state, the operation of the system? It's just VI phasor quantities. Also, breaker statuses, because this is also needed, right? And for this, you have what you called phasor measurement units, right? Now, non-operational data, it's required for times. So I should write non-continuous as and when needed, right? You only want this data when needed, right? So what kind of data falls into this category? It can be, you want to have records of fault switches, etc., etc., right? So how you don't require all of this data for for all the time, right? So don't happen continuously. It's not a continuous data. So just before the fault, during the fault, and after the fault, data is sufficient to determine the cause of the fault, right? And that is why it's called in non-continuous or periodic non-periodical data. It's continuous, right? And this is generally true for digital fault recorder. Your digital protective relaying also stores these data, and your circuit breakers, right? So all the data which is not required at all times, it's called non-operational data. It's only needed as and when the series of faults occur, and it records only for that time periods, right? And this digital fault recorder is used to record the fault pre-fault conditions, just before the fault took place, during the fault, and after post-fault conditions to monitor, right? Why do you need post-fault conditions? Because you want to monitor if the fault has been, if it has been removed, you would want to come back to how the switches were behaving. So when fault occurs, you sectionalize the area of the system, right? And if the fault has been removed, you need to auto reclose that the section as well. And for that, you need the data coming from them, right? What has happened post fault. Digital protective relays, they store data in the sense that relays, did the relay turn on, or did it turn on the switch? Why during the switch, when it was meant to open the switch or close the switch? And that is what digital protective relays use. They are used to isolate the fault. So fault recorders record this data. Protective relays, they just store instantaneous data and provide it to digital fault recorder to ice, and they isolate the fault when given. And circuit breakers are generally used to break the circuit. Let's, for example, if you have a feeder which is connected in a ring main form, you want to isolate that feeder, right? So you will turn on that circuit breaker so that the feeder is removed from the distribution system if it is causing faults. So this is what is used for just a second. Yeah. So this is what is used for your used as part of your data resources, right? So this is what WAM structure is, and this is how we store data. So we have PMUs located at different substations, and they have independent data storages as well. Uh, so these PMUs have independent data storages. They can store some amount of data locally, and then after that, they also submit this data to these phasor data concentrators, PDCs, which are in contact with the super phasor data concentrator, which is in contact with multiple PDCs, right? So this is what this hierarchical structure is. So what PDCs do is, what do PDCs do? One, the one main so they just don't store data. I mean, they store data. So you have to write, right? They store data from all the PMUs, store data from PMUs, but they are also given the ability to reject bad data. Let's say your phasor measurement unit is not behaving as it should, right? And it is sending you bad data. And your phasor data concentrator should be able to detect if this is a bad data, which is not something that your PMU should be giving, right? It can happen, noise can creep in or something like that. So before sending it to the super PDC, which can be viewed by different, controllers sitting at the remote stations, this is kept this is used to reject this bad data, so as you don't unnecessarily store and display this data to the operator, right? Third, hmm, Since you have multiple different samples coming from different PMUs, what you have to do is you have to align them with respect to their timestamps, right? So it aligns the data too. Right? Anything else that I'm missing? I think that was it, right? So this is what PDCs are used for, not just storing the data or concentrating the data coming from PMUs, but also to reject the bad data and align the data for the user interface, right? And this is used by this phaser information is used by the operator to make decisions sitting at a remote station, so that you know to have a complete observability of the entire network. So their application, as I told you here, their application is not just limited to transmission side, but also to the distribution side as well. So you can have VAMs applied to generation, transmission, and distribution system. For generation, you want to monitor the status of the generator, right? For that you can use, and also for the transient angle stability. So there is this uh, how to okay. So when a generator is giving power, it also stores some form of that power into its inertia, right? So what happens usually is, let's say a large loss of load happens, yeah, right? A huge chunk of load is removed from the system, right? So that generator uh, continues supplying that power. Why? Because of the fact that it still has stored some amount of data in form of inertia. And now if it continues to supply that, frequency dips more, and this is also called nadir frequency, to the point which it goes down, right? And this affects the rotor angle stability of the generator, because the generator is supplying power which it should not, because there is not enough load into the system. Who is going to consume that power, right? And to have that rotor angle stability, you can also use this PMUs, because it provides you data regarding the magnitude as well as your phases. Then you can have use this at transmission side to estimate state. When I say state estimation, it's nothing but to estimate mod of V and phase angles at different buses. If you know your voltage magnitude at different buses and phase angle at different buses, all other quantities can be derived, and that is why these two quantities are collectively called as states of the system. You can also use this as part of your load flow, your optimal power flow. If you have PMUs, you can store data, you can use this data to forecast and also to do economical load dispatch. At the distribution side, you can use it for restoration, bus voltage control. See, if you're monitoring any quantity, you can use it to, support that quantity as well. Let's say at a bus, voltage is dipping, right? You know from the PMUs that the voltage magnitude is dipping, right? What will you do? Voltage support device connected to that bus can be initiated, because you have data coming from that station, right? Similarly, line drop compensation, automatic reclosing. For feeder automation, you can use it to automate feeder switching, feeder voltage controls, active power, and anything at the distribution side, right? So these are all the application of VAMs. Now, at the smart grid monitoring, you have two essential kind of monitoring. One is monitoring of the oscillations, and monitoring the stability of the system, right? And for this, PMUs, as they give you the voltage and phase angle of any bus they are connected to, you can use them to check if there is any kind of to monitor any instances of negative uh, issues happening into the system. So this I already have discussed in the first lecture, but still we'll go ahead. So you have analog inputs. So your voltage and current waveforms, they are not digital in nature, they are analog in nature. When I say analog, so they vary continuously with time. Voltage and current, right? These are then sent to an anti-alias filter, where what you want to do is you want to remove high frequency component from the system. So your waveforms when sampled can have noise. So we'll discuss about sampling, but if sampled incorrectly, they can have noise creeped into the system, and you want to make sure that you remove that noise or that aliasing, because some, let's say, if your sampling frequency is not up to the mark, a high frequency component can creep in, and you want to reject that high frequency component, and for that anti-alias filter is used, which then sends it to an Paddy converter, which converts the analog to digital signal, which then phase locks it to the reference signal, which is your GPS, or this time reference, which is a cosine wave time synced to coordinated universal time. So based on your UTC, you have, or you already have, a cosine waveform synced to that UTC, and you want to make sure that whatever your digital samples that you have created, these are synced to this reference signal, which is then sent to a microprocessor, which manipulates the data to determine phasors, and then sends it to a modem, which broadcasts it to different communication systems. So when I said sampling, it can happen, as I told you, a frequency, a small higher frequency component can creep in. So what do I mean by high frequency component? So let's say this is your, at first figure, if you can see, this is your, let's say, a current, current waveform. And if you see, if you are sampling at 1 millisecond, your sample is at 1 millisecond. So if you're sampling at 1 millisecond, what does that mean? The frequency of sampling is what? 1 upon 10 raised to power 3, which is 1000 hertz or 1 kilohertz. So you're sampling at 1 kilohertz, right? And as you can see, these samples, if you want to draw a line through these samples, right? The sorry, this would give you the exact same curve of your waveform, right? As originally it was. But now let's say you are sampling at 2.5 milliseconds. This should be milliseconds, right? So you are having samples at each 2.5 millisecond. That means your frequency of sampling is how much? 1 upon 2.5 into 10 raised to power 3, which is 400 hertz, right? So you're sampling at 400 hertz, and as you can see, still your sampled waveform is still like a cosine curve, sine curve, right? And it has not distorted much. Why? Because it is still following the sampling theorem. So there is this theorem that your sampling frequency should be greater than equal to twice your frequency component of the maximum frequency component. If you have a sampling frequency greater than equal to twice the maximum frequency component, your sampled waveform would look much like your original waveform. Now, as you can see, if we check for this curve, right? So what is the time period? Can anyone tell me what is the time period? So the time period is how much? 0.02 seconds, right? So the time period is 0.02 seconds, or if you want to generate its frequency component, is it how much? 50 hertz, right? This is 50 hertz. 2000. Yeah, it's 50 hertz, na? Sometimes my mind stops working. Yeah. So it's 50 hertz, right? So you have a 50 hertz frequency of your original waveform. And as you can see, your frequency sampling rate should be at least greater than or equal to 100 hertz. And both of these are following this. Both of these are following this theorem. And if they're following this theorem, no high frequency component can creep into your sampled waveform. But let's say that you're sampling at how much? 0.02 by 8, right? And if I want to calculate its F naught, Fs, 8 by 0.02, which is how much? 8 by 0 is 400, right? 8 by 0.02 is 400, right? Hmm. 400 hertz, and what you want to do is you want to measure the fifth harmonic. So if you want to measure the fifth harmonic, your FM would be how much? 50 into 5, which is 250. So that means your sampling frequency rate should be at least greater than or equal to 500 hertz, right? And this sampling frequency is not greater than 500 hertz, right? And that is why what is happening is your waveform is not looking exactly like what you want it to measure, right? You wanted to measure the fifth harmonic, but now you can't, because there is this high frequency component. It seems like to be a fundamental frequency component, and that is why your sampling frequency should always be greater than or equal to twice your maximum frequency that is coming from your component from your signal, right? And that is why you use anti-aliasing filter, and these filters are also are nothing but your low pass filter. A simple low pass filter is your RC circuit, right? Why? Can you tell me why an RC circuit is a low pass filter? It is so because at higher frequencies, since your reactance is equal to 1 upon omega c, at higher frequency, the capacitor becomes short circuit, so there is no output in the signal, right? But at low frequencies, there is some impedance and you have some output at your terminals, right? And that is why your low pass filter, RC circuit, is a low pass filter. So this is what all happens with how your you how you get your P the how sorry, this is how your operations of the PMU look like. So what you do, you get your voltage or current waveforms, right? You time sync them with the GPS receiver. Then what you do, you perform a discrete. We will talk about discrete Fourier transform, but I'm just telling you what all happens. You perform DFT, which is called as discrete Fourier transform. So you perform this, you extract the 50 hertz component because your grid voltages and currents have 50 hertz frequency. Then you send it to symmetrical component transmission. What is symmetrical transformation? Symmetrical components are nothing but your uh, positive sequence, negative sequence, and zero sequence components of a waveform. And from this, you want to derive the positive sequence phasors, and these are then sent to your these are the output of your PMUs, right? Now let's talk about why DFT is employed. So, so your so your waveforms are continuous time signal, right? So these are continuous in time, and what you want the output to be is you want to sample this in such a way that you can extract 50 hertz component from uh, uh, this signal, right? So for that, what you do is you convert from time domain to frequency domain, and that is precisely what DFT does. It converts your signal from time domain to frequency domain, right? And that is what happens with DFT. Hmm. Right. So there are a few different kinds of DFT, but we'll talk about everything in detail. So what exactly DFT does? It discretizes your time signal into various frequency components. And how does it do that? Um, your original, let's say, is some A cos omega t, right? Your original signal was something like this, or I should say A cos omega t plus sine omega t, right? both cos and sin omega t. So it discretizes it, let's say, into k different components, which is something like this. Should I write Vk? Hmm. Vk Vn e minus j 2 pi n by n times k. I hope this is visible. I'll convert. Hmm. Hmm. So this is what your output of your after performing discrete Fourier transform to your continuous time domain signal looks like. Your continuous time domain signal is converted to a discrete components of discrete components which are sampled. Let's say for n, so this n is your number of samples. Vn talks about value of v at sample n, and k talks about frequency component, right? What frequency component you want to derive. So this is called a discrete, this is how discrete Fourier transform is used to discretize your signal into various components, right? So if I write in terms of this, so your Vk would look something like this. Vk is nothing but a real plus imaginary part, because there is this term. So how will it look like? It would be 2 by n equals to 1 to n Vn cos 2 pi n by n times k, right? And minus 2 by n summation n equals to 1 to n Vn sine 2 pi n by n times k. So this is how your um, uh, component looks like, where this is your real part and this is your imaginary part, and your magnitude is nothing but v real square plus vi mag square, and your phase angle would be tan inverse v real upon v imaginary, right? So this is how you can, sorry, it shouldn't be v real upon v imaginary, it should be v imaginary by v real, sorry, tan so this is how your um, how is you this is how it's used to generate your voltage phases by you doing a discrete Fourier transformation by breaking it down into different components, right? Now in full cycle DF, this whole procedure is called full cycle DFT. This whole procedure is full, this is nothing but a full cycle DFT, where k tells you about the frequency component. Let's say I want to talk about if let's say my lowest component is 50 hertz, k would be 1, and then appropriately multiplying it would be used. It's kind of like harmonics, like fifth harmonic, second harmonic, third harmonic. So that is what the value of k does. It is used to quantify the magnitude of kth harmonic in the system, right? Now, this is full cycle DFT, and as you can see, for full cycle, we have to do it for so the summation is from 1 to n, right? And we know that the sine or the wave or the sine or cosine wave, it's periodic in nature, right? And when I say periodic, it's just the opposite. For half time period, it is positive in the same size and negative for the same size, right? So we can exploit this property, and what we can do is we can have half cycle DFT too for the component, where we just do it for half cycles. And this is how half cycle DFT looks like. So your frequency component would now become 4 by n, since you are doing it only for half a cycle. It would be from 1 to n by 2 minus 1, and your Vn component e raised to power minus j 2 pi n nk, right? N by 2 or nk? It would be n only, right? So this is how your half cycle DFT would look like, right? Then there is one more thing called as cosine DFT. So why we are interested in minimizing the number of operations we are doing to calculate the frequency domains, the representation of our signal, right? Half cycle would do it for the half length of uh, the samples. Now with cosine, since we are getting both sine and cosine terms, and we know that sine lags cosine by 90 degree, right? So we can exploit this by, doing what? We can say that by getting how the cosine signal looked like and by 90 degrees before the present signal, we can get the estimate, right? So VK would look something like this. Just a second. Hmm. Cos of 2 pi n by nk, right? This is your, let's say, VC, right? Cosine term of your voltage, right? And we can say that your VK is nothing but VC plus J time VC n minus n by 4. So you see, for any given cosine, what we need to do is we just need to go back 90 degrees. Why have I done n by 4? Let's say for n full samples, you get 360 degree of waveform. Then for 90 degrees, it will be nothing but n by 4, right? N by 4 is nothing but 90 degrees, and that is why we do it. Then we have recursive DFT. Now, what does recursive DFT do? It is so when any new sample comes into play, right? When any new sample comes into your comes into is visible to you, you have to perform the DFT for all the samples that you have taken up until that point, right? To minimize the computational burden on your microprocessor, what you can do is you can remove the old value by performing it like a window. Let's say that this is how your, and what I'm saying is, sorry, you have a window of your DFT where you discard the old sample as soon as your new sample comes into picture. Let's say this. I should draw it for the same size. I don't know why I didn't draw it. Let me draw it for the same size. So if let's say this is how you will look like. So by same window, what I mean is when your new sample comes, this part is new, this part is old, right? And once you get the new sample, you remove that old sample from your recursive DFT window, and you perform it only for the window that you are calculating your DFT for, right? This is called recursive DFT, where you recursively remove the old values as and when new samples come into your system. So for this, the equation looks something like this. Vk is nothing but v vk dash, or I should say vk dash, which is your old one, plus 2 by n summation k n equals to 1 to n is the window of your samples, and vn e minus j 2 pi n by n k, right? And this is your present, and you want to add your new sample as well, which is k p plus r. Let's say your r is your new sample, right? and this should be outside, sorry, this should be like this. I was writing it for whole term, I should write it like this is much better. So this is how your new sample would look like. As and when your new sample arrives, you remove you remove the old sample, sorry, n minus r, this should be r, right? As your new sample arrives, you remove that old sample and just add it to your earlier estimated value. So this is what recursive DFT looks like. So as you can see, if you have a normal 50 hertz signal, these are the samples of how your of your waveform. Your magnitude would stay constant because your magnitude is not changing with time. It's just how the instantaneous magnitude is changing. Your RMS magnitude is not changing, which the phasor is calculating, and your angles are also changing with respect to the samples you are as soon as as soon as the samples are getting visible into your system. So this is what uh, is used to estimate the phasor values of your uh, uh, the quantities of interest. But there is one catch. As I said, k is nothing but the number of your harmonics, and the number of harmonics is only applicable to is only a positive integer which multiplies to your fundamental frequency. So for subsynchronous or below 50 hertz, you cannot use DFT, and you will not be able to get a complete picture of what is happening below 50 hertz frequency. For that, there is another method which is called as least square based estimation. Just a second. So what you do? So let me write below 50 or I should say synchronous frequency. DFT don't work, right? For that, LSC based estimation is used. Now there is one error in instructor slide. So when they are calculating the the pseudo inverse, they have inadvertently they have done a mistake over there. They have added some. I'll talk to you about that. But if you all had the chance of listening to that lecture, and if you wanted to do it on your own, derive everything what the instructor has done, you would have been able to catch that mistake. Anyhow, we'll derive it today in the class as well. But just checking if anyone has found out what the mistake was. So if someone has found out, just they can unmute yourself and just let me know. So how do the least square based phasor estimation work? So how your phase signal is supposed to behave. Let's say that the quantity you are interested in measuring is v or some x, and it behaves like cos omega t, right? Now what you do, you get the samples, and when you get the samples there will be noise, and when you want to do this estimation, what you want to do is you want to see without the noise, because if the noise is removed you will get what you wanted, the signal in its exact term, right? So if you measure it, let's say when you're measuring it, which let's call it y, this signal becomes x plus some noise, right? I'm calling it with respect to some omega, right? There is some noise into the system and you want to estimate this noise, right? But there is no way to know, because your measurements, you are only getting some, sorry, what is happening? Hmm. So there is some noise, right? And you want to remove that noise. So what you do least square error based phasor estimation. So let's talk about how you do it. So let's say you do some measurements, right? Just a second. Huh. So you do some measurement where it is like some a, or how should I? Okay, let's say it's a plus bt equals to m. right? This is how your measurement is supposed to look like, and you do it recursively. When you do measurements, you do it for multiple times, right? And because redundancy helps you in removing the in improving the accuracy of your results. So you do it for multiple times, so you get multiple different values of A's and B's. Similarly, an plus pn t is equals to mn, right? So you know how your measurements are, right? And what you want to do is you want to check how these measurements are different from your earlier value, right? And now you know, let's say you estimated something, your estimate is a cap, right? And you have estimated it for your uh sorry, your A's and B's don't change, your time is changing, my bad. And tn, right? So you estimated this A and you estimated this B, right? And you performed this again for multiple time steps. And you did it for n time steps. Now, based on this, you know there will be some error, right? From the original interpretation, this is from M1 to Mn. These M1 caps will vary by some extent, right? And that is called error. So if I want to write it, it would be something like this. A cap plus B cap T1 minus M1 is equals to error 1. Similarly, A cap plus B cap T2 minus M2 will be some error 2, and you perform it for n different time steps. Right. So you what you have is you have uh, okay. So you have an overdetermined linear algebraic system where you have more number of equations than your number of unknowns, right? So what you do, you so let's convert this into a matrix. So how will this matrix look like? It would be 1 t1 1 t2 for 1 tn, right? And this would be a cap b cap, which is then minus m1 mn equal to en, right? So what you have is you have an overdetermined uh, uh, linear algebraic equation with more number of equations than your unknowns. So let's check their rank. Sorry, their size. So this is n cross 2. This is 2 cross 1. This is n cross 1. And this is also n cross 1. So now you have these matrices, right? And it can be easily represented. Let's say the estimates were for your, so let's represent this by A, this by X, this by B, and this by E. It is written as A x cap. Let's A x cap minus B equals to E, right? So this is how your system would look like. Let's not call it B. If it's M, let's call it M only. And let's go with B. We don't have anything. Right, so this is how your system of equations will look like. Now, when I say that it is an overdetermined system, what you can do is you can optimize the error in such a way, find that value of these unknown x cap, which is this a cap and b cap, that can minimize the error. So, what you do, you perform an optimization of you minim pro, provide prom, this you convert this into an optimization problem where you minimize the error term. And how you do it is first you multiply transpose of each both side. So this would become E transpose E equals to A transpose X cap transpose minus B transpose A X cap minus B, right? And this ETE is nothing but your L2 norm squared cap t minus bt. Let's expand this as well. We don't have anything. So what will this be? This will be your at, okay, your aat x cap t minus a bt x cap, right? And then you have minus p at x cap t, and then you have minus btb, right? So you have, is it right? Can anyone just check? A at x cap t minus a bt x cap b at x t minus btb. Yeah, right. So you get this system, and yeah, there is one thing missing. Now I multiplied with this a, but not, yeah, foolish of me. Plus x cap at x cap t. Right. So you have this. Oh, why I just did that? This would be x cap only, na? Hmm. Right. So you have this system now, and over here, if you see, both of these terms are equal. Equal in the sense that these will be only a scalar, these are only a scalar quantity. If you can multiply both, if you can just check their matrix multiplication, this is n cross 2, this is n cross 1, and which is 1 cross n, a b t x caps. Just a second, this is what, oh sorry, this is a t x cap b minus b a t x cap, and then you have minus bta x cap, right? Okay, so you get these two equations, and if you see, both of them are scalar. Let's see. 1 cross n, then you have n cross 1, and then you have 2 cross n. Where is the mistake coming? B A T x cap t. This is n cross 1, na? And this is 2 cross n. This should be n cross 2. 1 cross n. This should be bt, na? Multiplied with bt. This should be bt at x cap tp. This should come here. It's multiplied this side, na? My mistake. This should be like this. So multiplied this, and yeah, now it's fine. So this is what? This is n. This is 2 cross n, right? This is 1 cross 2 now. Just a second, give me a moment. What has happened? P. It's coming like this. It should be bt x cap. If I take bt 1 cross n cross 2, and 2 cross 1, this is t. So this will be opposite of it, na? It should be p here, it here, x cap t. It should be. Oh, okay. Sorry. Yeah, my bad. X cap t at. This is how it should look like. Okay, so now both of these are now scalars. So if I check, this is what? This is 1 cross 2. This is 2 cross n. Sorry, I should use a different pen. This is 2 cross n, and this is n cross 1. So if I do matrix multiplication, what will this be? This will be 1 cross 1, right? This is a scalar quantity. Similarly, this is also a scalar quantity. You can check, and both of them are equal. If they are scalar and multiplication of the same matrices, even if transposed, these both of them would be similar. So if I write them, so what will this be? This will be x cap a at x cap t minus 2 times bt a x cap. Anything you want to write, right? Now what I want to do is I want to find that estimate value at which my error is minimum. So I'll write a minimum function, minimum at that x cap where my L2 norm is minimum. So how do we do that? We just differentiate this e function with respect to x cap and equate it to 0. Let's find out the differentiation. So this is a scalar term. Differentiation of this won't be an issue. This is 0, right? And this is just a linear multiplication, so this would be nothing but minus 2 bta. So minus 2 bta, and then you have this. So can anyone tell me what would be the differentiation of this function? Anyone who has an idea? So it's a quadratic function, right? It's a quadratic um, equation, right? Can anyone see that it's a quadratic equation? I just want you to see that this is a quadratic equation, nothing else. It's a quadratic equation in x cap, no? Anyone? So it's matrix calculus. It's a bit, tricky, but if you understand, it will be much easier. So its differentiation would, so this is what you call a quadratic function in x cap, and its simple differentiation would be nothing more than 2a80 x cap. You can check this on your own, but sorry, when you differentiate it, 80 comes before, so it would be 280a x cap, right? Similarly here, when you differentiate, the transpose are changed, it would be 280b. Yeah, my bad. Right, so you write this function here, it would be 280a x cap, which is equal to 0. And if you substitute both, it would be nothing but 80a x cap is equal to bta, and you multiply 80a inverse both sides. This would be 80a inverse, sorry, 80b. This would be, right? In the lecture, there is one more inverse sign added to this whole equation, which is wrong. So I just wanted to derive it once for you before, to see what really is happening in this system. Just let me check. Yeah, when it multiplies, the sum is changed. Okay, I forgot. Yeah. So this is how it would look like, and this is also called as pseudo inverse. This thing is called as a pseudo inverse. So in least square, methods are employed in, state estimation. State estimators employ weighted least squares errors, and this is a very important definition as per say for smart grids. And this pseudo inverse function is very easily implemented in MATLAB. It's called pinv over there. Any a matrix which is which can be written in this form is can be used to derive pseudo inverse for that matrix using pinv. MATLAB equivalent. Right, so this is how a least square based estimation is look like. So what you want to do is you want to minimize the estimated value of this. Sorry, you want to minimize the error by estimating correct value of this by having minimum errors. So that is what you use. So this is used when you want to find out for those frequencies which is less than the synchronous frequencies, right? There are other methods as well. There is a frequency estimation based on zero crossing. So based on how many zeros your sample signal is crossing, you can find out the frequency of that system. You by How do you do that? You just check how the slope is changing. If the slope becomes inward, it is one half of the cycle, and if the slope becomes same, it is one full cycle, right? So your frequency would be nothing but, if let's say for half, if let's say you're checking for one full cycle, it would be m f is equals to m minus 1 upon t2 minus t1, and for half cycle it would be m minus 1 by 2 1 upon, right? So this is used to calculate your So this won't be T2. I mean, then your half cycle needs to be calculated, right? So let's leave it like this. So this is how you can calculate the number of uh, frequency. And there is another way where you can get the frequency. It's through using the phasor rotation. By calculating how much this rotation has happened, you can calculate the frequency. As you know, omega is nothing but 2 pi f, right? So what you do to estimate f, what you check is how this omega is changing with respect to time. And just do 1 by 2 delta omega by delta t, right? And delta omega is nothing but your change in angle. How your angle is changing with respect to time, you just multiply 1 by 2, scale it by 1 by 2, and you will get frequency. So this is how frequency estimation, for normal systems and for all is done. And yeah. hmm Zero crossing based, phasor based, least square error, and DFT, all we have covered, right? So moving on. So the main purpose of detecting the whole this is not correct. It should be for m minus 1 by 2 only, but for 1 upon t1 minus t2 minus t1. Someone can check on slides. I mean, I don't remember the formula exactly, but I think this is the correct formula. It was m minus 1 by 2, 1 upon t2 minus t1. You can check it online. Check once, just. Right. Now coming to the next part. So next few weeks will cover protection, and um so we covered everything related to VAMs and measurements of phasors for monitoring, smart grid monitoring. But one more aspect that comes with increased penetration of DR is protection. Now what is happening is your system is evolving, your system is becoming more active, and for it becoming more active, you will need better protection schemes as well. And for that, you employ uh, uh, smarter protection systems as well, right? As we have already seen, your central utility, which functioned for top to bottom approach, where the power flowed from top to bottom, has now shifted to a more heavily distribution relying uh, uh, utility, where we have PVs, batteries, fuel cells, gensets, all in vents connected to your central generation as well. So your utility is expanding and it's becoming distributed in nature instead of becoming central. Right, and for that, what we need is we need to have better protection equipments too. And our relays have gone through a different have gone through different generations as well. Earlier, we used to have electromechanical type. In this electromechanical type, as the name suggests, what we used to do is we used to check, or we used to derive what the how the current was, how the armature current, it used to come, it used to have uh, coils, and and because it has coil, it has magnetic influence too. It was electromagnetic in nature. EM in nature, right? And what we used to check is how the armature current is varying, and if it varied with respect to a particular threshold, your this EM based relay will trip. Then we moved to a more static type, which was heavily reliant on your diodes, op amps, transistors, and all the static devices, right? So uh, these uh, yeah, where was I? Yeah, so these were a better alternative to your electromechanical type, because they didn't have any uh, this moving devices connected to, like for example, in electromechanical type there was a spring which sprung into action once it wanted to once the armature current was of a particular threshold. But in static, it was just op amps, and how they were used to derive quantities which would send signals to your uh, devices for tripping or not. Then we shifted to digital relays, which consists of microprocessors, and these microprocessors used to have algorithms which can detect when to trip, how to trip, and what to trip, right? And these digital relays are, new. I can't say new, but these are much more improved versions of their earlier predecessors, right? And but with their advantages, which we'll talk about in a bit, they also have a few disadvantages. Let's list them out. I just take them up. Okay, so this is bad, na? Hmm, much better. So their advantages are, so the cost. They are still expensive. I mean, they are not. It's not something like they are very cheap compared to the predecessor, but they are cost effective. Cost effective in a sense that they don't require over time they don't require much maintenance as their predecessors. So the predecessors required maintenance, while this does not require as much maintenance as their predecessors. So that is how they were cost effective. Second, self diagnostics. So they can estimate the health of the system. They have built-in self-diagnostic system where they can check if they are working perfectly fine, or if their health is perfectly fine. This ensures that they are reliable in nature as compared to their predecessors, right? They have auto reclosing function. So let's say uh you know uh uh, the relay issued a trip command, and some sectionalizers opened, and they sectionalized the fault. And now if the fault has been removed, what they can do is they can also have the auto reclosing function where they can reclose that section again by initiating a response to that. uh, Fourth, auto reclosing, self diagnostics, and cost. I forgot. There's one. Yeah. So they have storages. So as we said, these DPRs, digital protective relays, they consist of storage where they can store momentarily, or they can also have mass memory where they can store data related to fault, pre-fault, and post-fault conditions, so as to diagnose what really caused the disturbance, what really caused the relay to issue a trip command, um, and and other related parameters. Fifth, they are more reliable. So when I say they are more reliable, is in fact that because they contain precise algorithms with which they issue a command, they tend to be more reliable compared to their predecessors. But they have some issues. They have some disadvantages, which are EMI. So they are sensitive to electromagnetic noise coming from nearby high power devices, and it's EMI and yeah, shorter lifespan. So when I say shorter lifespan, is that because technological advancements are happening rapidly, the microprocessors can become outdated with the new technological advancements. So their lifespan is usually uh, for a particular application, their lifespan is sometimes small. So this is how the subsystem of digital relay look like for any digital device which sends signal in digital. Everything we have already covered in PMU's aspect, but we'll still see. So what they do, they require current and voltage data, which they pass to surge filters. What the surge filters do, they remove the surges that are present in these data. Like for example, some switches have closed, so there can be spikes in the data. So surge filters remove that surges. Then the signal is conditioned in the sense that can be inputted to the analog to digital converter. After that, analog to digital converter is used to convert that signal to digital, which is then timestamped to a sampling clock. Sorry, not timestamp, which is sampled using some sampling clock, and this is then sent to this processor, which is the brain of this relay. This processor contains all the algorithms that you want it to, any algorithms that you want it to, you want it to use for tripping and everything, which is then used to send, this digital output is used to send these digital signals, which are conditioned and sent to these contact outputs, where with these can be used to strip or send trip commands to a particular breaker or switch, etc. Similarly, if there are digital input contacts available, like for example, for any switch that has already been closed, so it needs to monitor that as well. So that these are sent using these digital contacts. And we have parallel ports and serial ports for communication with, with personnel. They can use laptops and configured devices which can monitor the health of the digital relay. And they have these memory blocks: RAM, ROM, EPROM, and mass memory, where they can store data. RAM is usually used to store momentarily the data from the system. ROM is an expandable storage, where we store the data for previous time occurrences as well. Erasable programmable read-only memory store the some kind of, like for example, your software updates and other things are used to store in this EPROM. So this is how a digital relays subsystems look like. And a relay cannot just take in values from the system. They use CTPT, current transformer and voltage transformer, potential transformer, to scale down it. So in India, according to standards, the recommended input current is 1 ampere or 5 ampere, and the for for voltages it is 110 volt phase to phase, or 63.6 volts phase to neutral. So this is the standard of Indian standard which we use. So you can see that you can either connect it directly across the main CT, or you can use an auxiliary CT to further tone down the output of the main CT and connect it to your relay. For potential transformer, it is kind of like a voltage transformer with potential divider circuit, where you tone down the voltage by using a potential divider. This, and then you send the signal to your relay, right? And I forgot why I got this. Yeah, same way where you how you sample this frequency is, every sampling frequency, it should follow this criteria to be able to possess the complete detail of the waveform that was inputted to the, right. And these are the three metrics in which we judge the performance of a relay: its reliability, its dependability, and its security. When we say reliability, that is, uh, there should be redundancy. When I say redundancy, so each relay is configured with a backup relay. Let's say a relay does not perform its operation, so uh, a backup relay which is used to support its operations is installed, which can initiate a trip or if at all required, if the earlier if the main relay does not do so. So by redundancy, we ensure that there is reliability in the system, and the metric to measure this is, okay. So the metric to measure this is number of correct tips so by number of desired trips, right? Is this correct? Can anyone tell me? Plus number of incorrect trips, right? So this is your percentage of reliability. Your reliability is used to measure what were the correct trips for the total of desired plus incorrect trips that it took. Total number of trips. Yeah, total number of trips. Yeah. Okay. Desired plus incorrect is the total number of trips that it has taken. Yeah, it's fine. Then we have forgotten that is why. No, it's okay. So dependability is used to measure how much percentages of the time the the relay trips when expected to, right? When it is expected to, how many times it trips. So it is number of correct trips by number of desired trips. So it is used to check how many times it has tripped correctly. Like say for example, it is number of correct trips is equal to desired trips. It is 100% dependable. That is, it is tripping as or when it should, right? Then it is security. Yeah. So security tells us that if let's say there is false tripping happening, right? If there is some false tripping that happened, how many times was it able to correctly trip compared to the total number of trips that it has taken, right? So here is where number of trips, total trips comes into play. Number of correct trips by number of total trips, right? Into 100. So how is it different from reliability? So in reliability, you are measuring that for the total desired trips and your incorrect trips, how many times was it, how many times correct trips happened, right? So there could be sometimes when it didn't trip at all, right? And you want it, you wanted it to be tripped. So that is why a number of desired trips was there. But here, let's say that for the total number of times it tripped, how many times was it the correct times it tripped, right? So in the first one, you could have missed the functioning of backup relay. Let's say, for example, when it was supposed to trip, but it did not because the backup relay tripped. So for that, the metric does not have total number in the denominator, but it is there in security because you're measuring for the for the total trips that it has undertaken. What were the number of correct trips? So this is how you measure the metric. So we'll discuss more in the coming classes. So it's the smart grid protection is dealt in detail by in this course, and you will see how modern protective systems have systems have evolved over the course of time to incorporate newer advancements in the technology. Right. So this is what I wanted to cover today and what has been covered by the instructor. So we discussed wide area monitoring systems. We discussed everything regarding how SCADA lags, where does it lag, what quantities do PMUs measure, and how using only voltage phasors we can derive any quantity which is measurable in the system, right? Then we talked about from where does PMU's dynamic or transient observability come into play. Then, what is the major differences between SCADA and PMU? The structure where we need in VAMs there are two important structures, which is data coming from different resources and your communication system. So your PMUs supply continuous data, whereas your digital fault recorders, your digital protective relays, and your circuit breakers provide non-operational data, that is periodical data. So, what are PDCs? What are super PDCs? We discussed. Then we discussed the application of VAMs, a PMU's basic block diagram, which was also covered in the first class. Then we discussed sampling, how sampling affects the frequencies and higher frequency components. What is an anti-alias filter and how we can filter out this component. We discussed in detail about what really happens inside a PMU. Then we discussed about discrete Fourier transform and phasor estimation based on discrete Fourier transform and least square error based methods. And then we discussed frequency estimation based on zero crossing and phasor based. Then we discussed about protection schemes. We just started with protection schemes and we'll discuss more on this in the coming weeks. So any doubts up until now? Any doubts? Now is the time to ask them. And there are not many people, so you can unmute yourself or you can, if you're shy, if you're not feeling like answering and you want to view the whole video before you ask, you can always use the chat box of YouTube videos, right? So if there are no questions, shall I move ahead? to questions. Yeah, let's move ahead. So, what is the sample rate of a digital fault recorder? So we discussed where a digital fault recorder is used, right? It is used to store pre-fault, fault, and post-fault conditions, right? So I hear someone. So you can always unmute yourself, right? You don't have to just. Okay, right. Store data related to pre-fault, fault, and post-fault conditions, right? Now, what should its sample rate be? Now, while discussing, I did not discuss its sample rate, but since it's recording, it's storing records for faults, right? Its sample has to be of very high resolution. When I say higher resolution, it's because the data needs to be of of very
Swastik.
needs to be of a higher number of
Hello.
samples per cycle, to really tell what is happening during the fault, so that during post disturbance analysis, the operator can use this data
Hello.
to estimate what really happened with during the fault, right? So usually it's between 64 to 356 samples per second, and since I did not tell you about it, that is why I just, it's cycle. So cycle is it's cycle, right? So it's even more. So the correct answer would be D. Like, so circuit breaker monitor data is also formed in. So can anyone tell me if Mayur Gupta can answer it very quickly? I know I did not cover, but he can tell. So circuit breaker monitor data is also formed in. Yeah, yeah, go ahead.
Swastik, you are not audible to me.
Yeah, you're
I'm
not
not
audible.
sure. Since last
I
two
can't hear
minutes.
you. Can you hear me? I mean,
Hello.
just a second, just a second,
Either
just a
there is a
second.
problem with my system or
Something is happening. I'm unable to hear.
hello.
Yeah, now you're audible. Yeah, now airdrop solved.
Yeah. Now it is.
Yeah, yeah. I was just a second, just a second. Why is there some sort? Just a second. What happened? Yeah, am I audible now? Can someone just unmute themselves and let me
Yes.
know?
Yes. Now audible. Last 2 minutes we lost.
Okay, something weird is happening. I'm unable to hear you,
I
but
tried to speak, but I was not able to. Then I raised the hand.
yeah, yeah. Now I'm able to hear you. Yes. So, so was the first question cleared? I mean, I don't know if first question was cleared or not.
No. You can start again.
Yeah, okay.
No, sir. I
Yeah,
was
yeah.
not there.
Yeah, I'll start. So, so what digital fault recorder does, it's used to store periodically the data, right? What happens during the fault, before the fault, and after the fault. So to store that data, yeah, just a second. Yeah. So for fault to do the post disturbance analysis, right? For post fault analysis, you require minute, a very high resolution data. So for minute instances, you require data, right? And that is why when I say high resolution, I mean you require more number of samples per cycle. So, for digital fault recorder, I did not tell this number because it's just a number, right? I forgot telling you this number. But for a digital fault recorder, this number is 64 to 356 samples per cycle. So you see, it's more than what your PMUs are providing. It's because it's used only for small for periodically when a fault has occurred, and to check, just to check and do the post disturbance analysis, and that is why the resolution is very high, and it's 64 to 356 samples per cycle. You can check instructor slide, it has been covered over there. She also talks about this, right? Next, the circuit breaker monitor data is also formed in. So all the data, which is stored for a in IEDs, or you say that what- for this digital fault recorders, these protective relays, all of these data is stored in a specific format. Can someone tell me, Mayur? I hope you know what the format name is, right?
Compressed format.
Comtrade format. So what is the complete name for this?
Compressed. I'm using it, but
It's common format.
it's there is a IEEE standard which specifies
Yes, yes,
what each bit would mean in basically generates a DAT file and one more file.
yes, yes. So
So
the
you can,
IEEE.
without a reader also, you can read that file.
Hmm, hmm, hmm.
If you are, means one would be the list of signals, another would be the data.
Yes,
So with the merging these two files, you can read it
yes.
uh, without any software. If you have a software, then directly you can read.
Yes, yes. And this format, as specified in an IEEE standard, it's called Common Format for Transient Data Exchange, and it's called ComTrade format. So you see, it's just the abbreviation, or some abbreviation of this word. So all the data, this circuit board breaker monitoring, this data fault, digital fault recorder, your digital protective relay, whatever data it stores, even the IEDs, everything is stored in this ComTrade data as specified in the standard. So you see, you don't store in just any format like .dat file or a .json file. It's stored in some format which is specified in standards, and that you have to follow. Next, which of the following phasor estimation technique can filter exponential DC components inherently? So I just
That
told you.
is sorry, I'm interrupting.
Yeah, no.
That is done so that there are multiple vendor relays, say
Yeah.
GE, Siemens, and Micom, and so many vendors,
Yeah, you
Schneider.
you want to
So all
standardize.
generate a similar file,
Hmm.
so that it's like a universal format which can be read by anyone.
Hmm.
Otherwise, everyone would generate their own format, and it would be difficult to exchange this kind of information.
Yes.
In case of any event or eventuality, it is required at times to read hundreds of relays at a grid scale.
Hmm.
So, in that kind of thing, it is easier to collect this data in one format and be read by any person.
Yeah, yeah, exactly. So you have many vendors, and you want to have a standardized format of this data, right? So as to it can be read by anyone, any different relay of different vendors, right? So for that standardization, you use a common format, which is Comtrade format, which is also called common format for transient data exchange, and it is specified in IEEE standards too. Any electrical system standards, they generally take IEEE standards. Like for example, three standards we have covered up until now, right? One is IEEE 1547, which talks about interconnection of your this DRs to distribution system. The other is IEC 61850, which talks about substation automation. And then your standards related to IRIGB, let's say for example, which talks about the GPS signal and that time synchronization of the GPS clock. And then you have this for a synchronized. I don't know the exact numbers. Numbers you can already always search, right? Numbers you should not remember, and I don't want you to remember any numbers, right? I feel numbers should not never be remembered. They can always be. Why would you remember the 64 to 356? It means nothing to us, but still, I mean, I'll leave it all to you. Next, which of the following phasor estimation technique can filter exponential DC components inherently? Can anyone tell me? So we studied where DFT lags, right? And where LSEs come into play and help in correcting what these DFTs lack. One thing I forgot mentioning. So there is one inherent disadvantage in this scheme, right? So that inherent disadvantage is matrix inversion. So it requires inversion of this ATA, and let's say this ATA matrix is not, it's not a square matrix. So converting this won't. Generally, ATA would be convertible. I mean, it's n cross m times m cross n. It will always be that. But let's say that somehow it will always be, but let's say sometimes what happens is you generate this ATA and it is not invertible, and sometimes it can be of a very huge matrix too. So inverting that huge matrix is not always possible, right? So ATA would always be invertible, I'm sorry, but sometimes this can be so huge that inverting it would take a lot of computational time, right? So this matrix inversion is something that generally is a inherent disadvantage of the scheme. So I just wanted to talk because I missed that. There is a lot of information covered, so you probably tend to miss a few. Right. So when I was talking about this, I talked about where the DFT techniques lack. They lack because they are not applicable to subsynchronous components of frequency components in your signal, and an exponential DC component which is generally having a frequency which is just zero, right? It decays exponentially. So what usually happens is this is a subsynchronous component, right? And for that, what kind of estimation technique would be much more suitable? What do you think? Would DFT technique be suitable for this?
No, no.
No, right? And for that, we use least square estimation technique. What we do is we minimize the error, the square of the L norm error term, L2 norm error term, to estimate the correct values of our system. Next, in GPS, each satellite covers dash of the globe. So this is also numbers. Yeah, 42. And how does it come? So we have 24 satellites in 6 orbits for GPS. And this orbit is around 10,000 miles above. And each satellite covers 42% of geographical area. Next, in the WAMS technology, non-operational data is used in. I just covered non-operational data. What is non-operational data and where it is covered? So here I covered, right? So you have two kinds of data: operational data, where you have continuous stream of data, and you have non-operational data, where you have non-continuous and periodical data, right? Where, like for example, digital fault recorder or digital protective relays, right? And circuit breakers, monitors, sorry. So the correct answer for this is all of the above, as said by Naki Akhtar. And next, if a signal has a fundamental frequency of 100 hertz and it is sampled at a sampling frequency of 30,000 hertz, then the number of samples per cycle is. Can anyone tell me how many number of cycles will there be?
300.
Yeah. So the number of cycles is nothing but sampled frequency upon fundamental frequency, which is 30,000 divided by 100, which is 300 samples. So the correct answer is B. Right, and next, a 100 hertz volt signal is sampled at 5,000 hertz. Then the phase angle between two successive phasors estimated by DFT is. Who can answer this question? Very easy. So if a 100 hertz signal is sampled at, let's let's assume that this signal is 100 hertz, right? And it is sampled at 5,000 hertz. That means number of samples will be how much? 5,000 divided by,
50.
right? So you have 50 samples coming from this sampling, and these 50 samples complete how much? Okay, so for 360 degrees of this,
So 360 by 50
yeah,
probably.
360 is n, and for any phi, 360 by n, which is 7.2, right? So it is 7.2 degrees.
7. Right.
Next, the relay percentage of security is defined as, I just covered. So you want to ensure that how many times it is it how many times it tripped, sorry, how many times it was a correct trip by total number of trips, right? So it's C, correct. Next, the advantages of digital relays are, what are the advantages? Whenever you see advantages, right? It's I've always seen all of the above. I mean, there can be instances, but generally the answer is all of the above. So they are self-checking. That means they have self-diagnostics. They are auto reclosing. That means once the switches sectionalize an area, they can also reclose that area to, you know, uh, and they can be used to integrate the system. And this is the advantages of digital relays. Next, in the signal, first zero crossing occurred at 0.01 and the ninth zero crossing occurred at 0.05. Then the frequency of the signal is. Who can tell me? So I've forgotten that formula. Was there a 2 or not? Someone has to tell me. Hmm, just a second. 8, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 0.01 and this is 0.09, right? So that formula was how much? Oh, someone has already answered. 50 hertz. So
0.05 or 9?
0.09. Oh, sorry. 0.05. Sorry. Yeah, sorry. Right. So, Naki, the answer is wrong. I would appreciate if you could, just check it again. So the formula was, if I am not wrong, m minus 1 upon 2, 1 upon tm minus t1. Someone has to check. Right. So it says that the number of zero crossings are 9. So 9 minus 1 by 2 upon 1 minus 0.05 minus 0.01. So this is 4 upon 0.04. 4 divided by 0.04. So the, oh, why am I doing 4 upon 0.04 is nothing but 100. So the answer is 100 hertz if this is correct. Let's check. There's one more way to check this, right? So you see, there is for 8 zero crossings. Yes, he's saying yes. Oh, the formula is correct. Yeah, but let's check it once. Okay, so for 8 zero crossing in between, you took 0.04 seconds, right? So 0.04 seconds for 8 zero crossings. That means for each zero crossing, you took 0.005. So that means this was 0.015 and this was 0.02, right? And since the time period is 1 upon 0.02 minus 0.01, yeah, 0.01, which is 100 hertz. So the answer is correct. It's 100 hertz. This formula is correct. Yeah. Right. So you can do it that way as well. You just check what is the total number of times the zero crossing has occurred in between and how much time it has taken. Based on that, you can always find it, right? And I just did the same exact thing. I don't know why I went with that. Fine. Let's go ahead. In digital relay, dependability is the ratio of what? So, what does it mean to be dependable? That means it trips correctly for the number of desired trips it is needed out of it, right? So, the answer is no. This is reliability. It shows that even by redundancy, when a backup relay has tripped, it tells you how many times it should have tripped. So, the correct answer is B, right? So the number of desired trips were 100, but it trips just 99 times, right? It was 99% is the dependability. Next, in the context where DFT phasor estimation does not involve estimating which of the following. So a phasor estimate provided us with what? Can anyone tell me? Let's go back. So
RMS value?
no, it provides this RMS value, na? The RMS value is already it's the magnitude that it gives, na?
Okay.
Okay, let's check. Right. So this, right? When you decompose this into samples, and you apply DFT, you get a magnitude and a phase angle, right? And what happens is that this magnitude that it gives is generally the RMS value of that magnitude, right? Let's say, for example, this is the peak value, right, of the waveform, whatever this waveform is of. It gives you the xm by root 2 value when you decompose it, right? So this Vn over here, whatever this is, by when you uh, expand it, it gives you this value xm by root 2, right? And this angles which they give, it's generally varying with respect to your what you say, with respect to your samples, right? It does not give you the instantaneous value of the angle at time t equals to 2. What is the value of the angle? It cannot provide because it may not have sampled at that time. So it can give you the RMS value. If it gives you the RMS value, right, let's say it provided you with V, you know the RMS value is Vm by root 2. So you can derive the peak value of the signal too. If RMS is known, peak value is known. It's just scaled by a factor of 1 by root 2, right? What is not known is the instantaneous value of the angle. And that is where phasor estimation fails, because it cannot provide directly the instantaneous angle of the signal. It can only provide if it has taken the sample at that instant. Next, which component of synchronized phasor measurement systems creates a record of recorded data? Yeah, can anyone answer this third question? So, was everyone clear with B, right? The second question, in context with DFT, phasor estimate, what does not involve estimating? Okay, so Akhtar gave the answer. Yeah, it's PDC. PDC is used to store the data. Now, coming back to the second question, is everyone clear how it cannot give instantaneous value of the angle? Mayur, are you clear?
Yeah, okay.
Hmm. Fourth, which of the following is designed to isolate the area of faults and reduce the impacts of faults from other parts of the system? So your DFR is digital fault recorder. Your DPR is digital protective relaying. Your CB, just a second. Your CBM is circuit breaker monitor, and your CBR is, I hope it is recorder only, right? So which of the following do you think
B.
provides isolates a fault?
DPR.
DPR, right? The relays are used to isolate the area of faults and reduce the impact. A central PDC is installed at NLDC. Where is NLDC
Sir, what
located?
about circuit breaker? Sir,
Uh-huh.
what about circuit breaker? Circuit breaker.
So a circuit breaker is used to isolate, but it is kind of like a switch, right? So the relay provides you the information which is then given to a circuit breaker. Circuit breaker cannot operate on its own. The relay estimate the fault, how the currents have changed, how the magnitude of current has changed, and based on that, it initiates a sequence where it asks a circuit breaker or a sectionalizer or a switch to trip so that the area is isolated. So a digital protective relay is used. So circuit breaker, it's circuit
I think
breaker
that is
monitor and
the
recorder. It's not
right
circuit
answer,
breaker.
but that option is there is no option for that. No,
Which option? Yeah,
it's
the
a
circuit
circuit
breaker is
breaker
not. Yeah,
monitor and
I was
recorder.
coming.
No,
Yeah,
there is
I
no
was coming.
circuit breaker.
Yeah, I'm coming to that. So, and at the end, circuit breaker monitor is, it's the option is circuit breaker monitor or recorder. There's no circuit breaker which will be the answer to this. But still, the design, I mean, yes, circuit breaker are some extent can be used to isolate, but it comes from the relays. But yes, these are monitors and recorders, not circuit breakers. But if your question was if circuit breaker is an answer to that, could be, but not in the context. Fifth, A central PDC is installed at NLDC. Where is NLDC? So it's not NLDC anymore, it's Grid India or Grid Controller of India Limited. So where is it? Does anyone know? It's in Delhi. Fifth, according to the sampling theorem, the sampling frequency must be greater than what? The highest frequency to be sampled. I just covered, right? The sampling frequency should always be greater than twice the maximum frequency component. So the answer is 2. Yeah. Next, recursive DFT does what? I just told you, right? In between, what does it do? It reduces the number of mathematical operations, right? You don't have to continuously do for all the samples you have generated. Uh, you can delete the previous samples as and when the new samples come into picture. So it reduces the mathematical operations. Last, phasor estimation based on least square method can be applied for signals with decaying dash component. So we covered a question with this, right? So it's just the answer to that question. Here we covered it, right? Somewhere. Yeah. So can filter, yeah, exponential DC components, right? So with decaying DC components. So this is all what was covered today. We discussed VMUs, how we do estimation of phasors, the frequency, wide area monitoring system, and all. And we discussed about we started our discussion on smart grid protection. It's not just it's a very wide topic and will be covered in the coming weeks as well. Are there any doubts for this class today? If not, we'll end the call here. Are there any doubts? Okay, not a problem.
Yeah, thank you. Thank you so
Yeah,
much.
thank you everyone for being present. Yeah, bye.